Today we will have a new topic, which is the capacitors and the inductors. And we will start by talking about the capacitors, and then we will talk about the inductor. Now, why this topic is important and what is the relevance of this in this course? One thing is the following. If I have a circuit, let's say I have a voltage source, and I have a resistance, another resistance, and let's say a switch to switch on and off the circuit, which is basically the case. And assume the switch was off. The moment I open the switch, immediately I equal to zero, because the resistors, which is the only passive elements we learned so far, cannot store energy. So this is one important aspect of electrical energy, that in many cases we want a device that can store the energy to be used later on when I don't have the supply of the power. And the capacitors and the inductors, both of them are energy storage devices. So we will learn how they store the energy, in what form they store the energy, and if they are in a circuit, how we can analyze this circuit and find how much energy is stored. So that is one aspect of the capacitors and inductors from the perspective of the circuit analysis. Now, from the perspective of the sensors, there are sensors that are based on capacitive nature and inductive nature. Now, what all the sensors or most of the sensors we learned were resistive sensors. The strain gauge was a resistive sensors. Most of the temperature sensors were resistive sensors. And we have seen some other even examples about different types of resistive sensors. So resistive sensors are based on the resistance, how it works. So capacitive and inductive sensors, on the other hand, it depends on how the capacitor and how the inductor behaves. But we will only cover sensors about capacitors, because inductive sensors are a bit hard to explain without being in person, without going to the lab. So I eliminated the sensor that based on the inductive sensing, and I only kept the ones that about capacitor, which will be covered at the end of this set of notes. Now let's start with the capacitor. What is a capacitor? Capacitor is basically a passive device. Passive device means it does not generate energy by itself. As a matter of fact, it stores the energy and then can be used later on. But by itself, it does not develop its own energy. So it stored the energy. Now, in what form? It stored it as an electric field. So the energy that's stored, it's converted, or it is stored as an electric field inside the capacitor. So what is a capacitor basically? We have actually two conductors. One conductor will be energized, one conductor will be grounded, so its voltage will be equal to zero. So that's basically the two conductors, and in between them there is an insulator, or what we call a dielectric material. What is a dielectric material? It's a material that does not allow the current to go through. Like, for example, rubber. Rubber is a dielectric material. Wood is another dielectric material. So this material will not allow the electricity to move, because the electrons are attached strongly to the atom. So they, even with the influence of the electric field, they will not be able to move. Unlike the conductors, where the electrons are loose, so easily they can move in the conductor. Okay. Now, capacitor could have different shapes. Like, for example, here, this parallel plate. So here, the parallel plate, one side will have the high voltage connected to it. The other side will be grounded. And in between, there is a dielectric material. And we will see with permittivity, we will see this permittivity in the coming slide. Or it could be a coaxial. So inner this is the one that will be energized with electricity. Outside is grounded, and in between them there is dielectric material with the permittivity, which is a property of the dielectric material, and I will come to it. Now, what is the relation that governs the basic elements of the capacitor? We have the charge. This is the charge that is will be stored there. We have what we call the capacitance. Capacitance is like resistance in the resistor, and then this is the voltage that you apply. So this is the voltage, which something that we know. This is the charge, which is how much. This is the whole idea. We need to have some charge stored there. But then this is the capacitance, which is something for us new. What is this? C is equal to what? Now, it depends on the shape of the capacitor. We have different formulas for C. So, for example, for parallel plate, C is equal to epsilon A divided by D. Let's start with A. A is the cross-sectional area of the plate. So the bigger the plate, the more capacitance you have, the more charge you can store. D is the distance between these plates. So this is D, the distance between this is your D. So the D is actually the distance between the plate that is energized with high voltage or with voltage, and the other plate that is grounded. Now, what is this epsilon? Epsilon is a material property called permittivity. And basically it's equal to epsilon 0 times epsilon r. For short, we say epsilon. Now, epsilon 0 is a constant. This doesn't change. Epsilon r is the material property. We call it relative permittivity. Now, this relative permittivity is the ability of the material to store a charge. Without going into depth in physics, that how this is, how we can go from the molecular level to understand this permittivity, we don't need to go that level. This is usually people in electrical engineering who are studying some physics about the material. That's not our concern. So all you need to know that this is the epsilon r is the ability of the material to store energy. And as you can see here, this is a constant. So as epsilon r, the higher the epsilon the r, the more the C is, and the more the charge that you can store. That's all you need to know. Now, for dielectric material, which is typically the material used in the capacitor, is between 2 to 6, something like this, in this range. So it's a small number. It's not a big number. Now, for a cylindrical capacitor, the formula is different. But again, the formula depends on two things. The geometry, so here we have two parameters for the geometry, the cross-sectional area and the distance. Here we have the length, the inner and the outer radius, R2 and R1. So these are all dimensional types of parameters. And also we have the epsilon, which is the same as this epsilon here, which is the property of the dielectric material between the two electrode, the energized one, the unenergized one. Now, as I said, if I want to have a bigger capacitor, which is usually I do, how I can do that? These are the three parameters that I can play with. I can increase epsilon, but as you can see here, we have limitations here. Except recently now, in the last few years, we have something, as maybe you have heard the term, nano technology. And this nanotechnology has a lot of applications. One of them is nanomaterial. And these nanomaterial basically are material that, for the dielectric perspective, will have very, very high dielectric constant, thousands. and there is no need to go through the physics that how this can happen. Okay, but now we have what we call supercapacitors. These are available in the market, and those supercapacitors is based on basically on nanomaterials or nanotechnology, and they can have very high value. But this is only recently. Before, we have limitations here, and the only two parameters we can change is the cross-section area and the distance. Now the distance, we can bring it closer and closer the plates, or make this closer and closer. However, we have a limitation, because if we make them too short, the distance, because there is one side high voltage, the other side there is a ground, so there is an electric stress. So if the distance is a bit small, you could have a breakdown. So you have to you have some limitations on that also. Another parameter is A, increase A. But how big we can increase A? Also, we have some limitations because of the space around us. We cannot have just A as big as we dream to be. So one way to come up with this is to have the capacitors. They are parallel plates, but instead of having them as a parallel plate, we have them as such. Basically, we roll them, so they will be like a cylinder. So they will not be very big barrel plate, but we roll them as a cylinder. And this is how they look like, the cylindrical ones. Okay, so they are reasonably uh, sized. And these are some other forms of capacitor. These what we call them ceramic capacitors. They are made from ceramic, and they are used for very high voltage application. They can withstand thousands of volts. Those ones, on the other hand, they store more energy, but they work at a low voltage. Let's say at 110 volt. Those work on tens of thousands of volts. So they are different applications for each one. Now let's start the real deal now here, and let's start talk about circuit. Now that was just an introduction. Now we want to see how we can deal with the capacitors. At the end of the day, we want to deal with the voltage and the current. This is our main components in the circuit. I don't need really to work with a charge, because a charge is something very hard to measure. On the other hand, current is something I can measure using the ammeter. So the charge, they have very sophisticated devices that are used in certain applications, but not with us. Now, to start with, this is how the capacitors looks like in the circuit. The two parallel plate uh, basic capacitor, which is one of the most fundamental and old capacitors. So the symbol of the capacitor took that, and you'll see here this is one straight, and the other one has some sort of slope a little bit here, and this is not by mistake, this is intended. You will see that for capacitors used in DC voltage. So far we work only in DC voltage, we don't work in AC. Later on we will work with AC. When you work with AC, you will see that the capacitors like this, both lines are straight. Why is that? Why is this line is have this slope? This is to tell you that this capacitor, this terminal has to be connected to the positive, and this has to be connected to the negative. What if I reverse? If you reverse, the capacitor will be exploded. So if you go to YouTube and search for explosion of capacitors, wrong connection, there are many cool videos, but don't try this at home, of course. That when you reverse the connection of the capacitor, they explode. So this is intended to be. So you have to know where is the positive and where is the negative when you connect them in DC circuit. Now we use the passive convention. So if the current direction coming like this is a passive device, so the current will enter the positive terminal. This is exactly the same as we did before. Now the capacitor could be in charging mode or in discharging mode. Basically, in this course we will deal only when it is charging. We will not deal with it when it is discharging at all. This is dealt with a different topic that we are not really interested in this course. Okay, now we said that here the basic relation we have so far, Q equal to CV. So we have Q equal to CV. But as I said, this is not really something we are really interested. So let's move on. So let's take the derivative for both sides of the equation. So this becomes equal to dq by dt equal to. Now, C doesn't change with time. C is the capacitance. It's, as we have seen, it's actually a function of two things: dimension of the capacitor and the material of the dielectric between the two electrodes. So this stays as it is. When you multiply by a constant, this doesn't change. Then we have the voltage. So this will becomes dV by dt. Now, but what is dq by dt? That we know that the current is basically, we mentioned that at the beginning of this course, is basically is equal to dq by dt. The current is the rate of a change of the charge. So this means that your current I is equal to C dV by dt, and this is the fundamental law in a capacitor, that the current is equal to the capacitance times dV by dt. So if I know the voltage across the capacitor, if I take the derivative, multiply this with C, then I can find the current. What if I want to do the opposite? I want to find the voltage from the current. So this is simple. So 1 over CI is equal to dV by dt. So it means that your dV is equal to 1 over CI dt. So if I want to find the voltage, I will take the integration for both sides, and I will integrate from T0 to T1, let's say. So I need to add the initial condition, and this is equal to your voltage. So if I want to find the voltage of the capacitor, knowing the current, I will take the integration from a certain time T0 to T1, from this time to the time I want to take the integration, and I have to add the initial conditions. So if the capacitor was initially doesn't have any charge, it means it doesn't have any voltage, then this will be equal to 0, and the voltage is basically is equal to this formula. Now, if I have a DC voltage, as this is the case, applied to a capacitor, this voltage basically is constant, doesn't change with time. So your I is equal to C dV by dt. So your current in a DC is equal to 0. I will equal to 0. This current I equal to C dV by dt, but dV by dt is equal to 0. So if this is equal to 0, then the capacitor in DC circuit, when it is charged, is equal to open circuit. So how to represent the capacitor in a circuit? We represent it as an open circuit, which is something very interesting. That when I model the capacitor, I will just change it, remove the capacitor, and substitute, as we will see, as just an open circuit. Another thing is the following, that the voltage cannot change instantaneously in the capacitor. Cannot. This is against the physics. Why is that? Let's see. If the voltage is changing like this, going from 0 to maximum voltage at no time, okay, so it means that the current, which is equal to C dV by dt, what is the slope of a vertical line? The slope of a vertical line is infinity. So the current becomes equal to infinity, which is physically cannot be. So you cannot this again is the physics, you cannot have a voltage across the capacitor that change instantaneously. Otherwise, you will have current that goes to infinity, so that's not possible. So always the voltage will have certain rise time. So something like this. So the voltage will take certain time. So your dV by dt will be like a definite number, not an infinite number. Now let's have some examples here. So the first question is, what is the voltage across a capacitor of 2 microfarad? So we have C is equal to 2 microfarad. And 2 microfarad is equal to 2 times 10 to minus 6 farad. Holding 10 millicoulomb of a charge. So your Q is equal to 10 millicoulomb, which is 10 times 10 to minus 3 coulomb. So I'm always trying here to change everything into farad, which is the unit. Maybe I have forgot to mention that. The unit of the capacitance is actually a farad, the unit of the charge as we know it as a coulomb. Now we want to know the voltage. Now we know Q is equal to CV. This is my Q. So your V is equal to Q divided by C, which is this 10 times 10 to minus 3 divided by 2 times 10 to minus 6. This will equal to 5, and this will be 1,000. So this is 5,000. And 5,000 what? 5,000 volt, because I'm fighting the volt here. So this becomes volt. Okay, so this is as simple as that. Second question is the current. We have the current through a 100 microfarad. So we know this is C of the capacitor is equal to 100 microfarad. We are given the current I. Okay, is a sinusoidal. Now this is not a DC. This is a sinusoidal. We want to find the voltage across this capacitor at t equal to 1 millisecond and at t equal to 5 millisecond. And we will assume that the initial condition of the capacitor, they have no voltage. V is equal to 0. Now, this is the relationship that I derived, that if I know the current, and if I want to find the voltage, I will take the integration. So from this, you can say that V is equal to 1 over C. Now, what was C? C is 100 microfarad. So this is 1 over 100 times 10 to minus 6. Always make the capacitance in farad so that the unit will become smooth. You don't need to worry about, oh, this is micro, this is milli. Then if you start to mix up things, then you will have problem with the final unit. Now here I want to find at t equal to milliseconds. So I will integrate from 0, which is the initial point, until 1 millisecond. Now this is millisecond. Okay, millisecond means this is equal until 1 times 10 to minus 3. And then we will have I is given to us, which is the 50 sine, the sine function, 120 pi t dt. So all of this is nothing but your current, your I, which is given, plus V at t0, voltage at the initial condition, which is V at 0. This is your starting. You want from 0 to 1, and we know that this is equal to 0. So now becomes a mathematical problem. Basically, we need to find the integration of this. Hopefully that's not a hard thing for you guys. So this is V is equal to, I will take 50 to the other side. Okay, so this becomes 50 divided by 100, and this is 10 to power 6. So this will cancel. This becomes 10 to the power 4. Okay, now what is the integration of a sine? It's a minus cosine, and we need to divide by this. So we'll take this out, the integration. So this becomes 120 pi, and there is a minus sign here, and then we will have cosine 120 pi t from 0 to 1 times 10 to minus 3. Then this is like a limit integration. Just this becomes cosine. This is a constant value outside. So cosine of this minus cosine of 0. So if you do that, find the value. So you'll find this is equal to 93.14 millivolt. Now, says also I need to find the voltage after 5 milliseconds. So this is the voltage after only 1 millisecond. Now again, I will use exactly the same formula and I will have the voltage is equal to 1 over C. Doesn't change. So 1 over 100 times 10 to minus 6. Now I want to do the integration until t equal to 5 milliseconds. Now I have two approaches. The first one, I will take the integration from 1 millisecond, 10 to minus 3, to the 5 millisecond, 5 10 to minus 3. And then I will have here 50 sine 120 pi t dt plus the voltage at the initial condition, which is this one now, which is at 1 times 10 to minus 3. And this voltage is I already calculated that, which is this voltage. So I will insert this an initial condition and I will take the integration. Or I can do exactly the same thing, but I will change the limit. Instead of going from 1 millisecond to 5 millisecond, I will go from 0 to 5 millisecond. And again, this will be exactly the same, no change here, 50 sine 120 pi t dt plus v at the initial condition, which is 0, which is equal to 0. So either if you solve it this way or that way, you will get exactly the same answer, which is equal to 1.73636 volt. In both cases, you will get exactly the same. Let me see if you have any questions here. Okay, good. So we are thinking the same, Kelly. We are thinking the same way. Okay, excellent. Let's move on. So this is everything here is the detailed answer. Okay, this is I would say the previous question, and this question you could say this is like question number 2 in the final would be like I gave you the capacitor current or voltage, and I ask you to do the other, or I give you a graph like this one. So in this graph, I give you the voltage, and I want to find the current, giving this is your C. So if I give you the voltage, and if I want the current, so from this we can say that the current is equal to C dV by dt. So I need to find this function so that I can take the derivative. Now I give you as a curve, not as a function. In the previous example, you are giving it as a function, so you take the integration or you take a derivative of function. But what if I give it to you as a curve like this one? How I can do the derivative? Then you have first to find the function, and you have here two lines from 0 to 6 milliseconds. We have one line here, and then from 6 to 8 we have another line. So we need to find the function of both of them. Now this is a straight line, so for the straight line the equation will be that the voltage equal to the slope times t plus a constant a. But since we will take the derivative of this, dv by dt, a will go to 0. So I don't need to find the constant. I don't need. What I need to find is only the slope, because your dv by dt, actually, your dv by dt is equal to m. And what is m? Is your slope. So basically, you need to find the slope from 0 to 6, multiply it by c. That will be the current from say 0 to 6. And then find the slope from 6 to 8, multiply it by c, and that will be the current, and that's it. And then we have a 0, so everything will be equal to 0. So let me draw this here as a straight for the y and the x axis. So this is your current I, and this is your time t. In millisecond, we will follow the same thing. So we have here up to 6, and then here we have up to 8. Okay, so let's find the slope. What is the slope? The slope is the difference in the y by the not the summation, sorry. It's equal to, the slope is y2 minus y1 divided by x2 minus x1, the difference in that. So we can select any 2 points. We have these 2 points. So your slope from 6 to 8, so from 0 to 6 millisecond, your slope equal to 24 minus 0 divided by 6 millisecond. Remember, this is millisecond minus 0. So this is equal to 24 divided by 6, which is equal to, basically is equal to 4 times 10 to the power of 3. This is your slope because this is millisecond. So this is equal to 10 to minus 3. So this becomes 4 equal to 4 times 10 to the power of 3. Now, what is the current? I here is equal to C. C is 5 times 10 to minus 6 multiplied by 4 times 10 to the power of 3. 5 times 4 is equal to 20. 10 to minus 3 times 3 is equal to 10 to minus 3 is equal to 20 milliamps. So you can keep it as this, as an amp, or you can keep it as 20 milliamps. It's up to you. Okay. So from 0 to 6, we will have here as if this is in milliamps. So this is equal to 20. Now we'll go with the slope from 6 to 8. From 6 to 8, the slope, again, we will select 2 points. So we can select, it doesn't really matter which 2 points you select. So if you said, if this is your x1, y1, this is x2, y2. So the slope, what is your question? Let me check here a second. What is the F? Farad. F is the Farad. Yes. Thank you very much, Kelly. Thank you very much. So 6 to 8. So y2 is equal to 0, 0 minus 24 divided by, so this is x, y2 is 0. Here it is. So this is 8 and 0. Here it is 6 and 24. These are the 2 points. So 0 minus 24 divided by 8 minus 6 times 10 to minus 3. And this is equal to 24 divided by 2, which is equal to 12 times 10 to the power of 3. So now here the current I in this period will equal to the 5 microfarad, 5 times 10 to minus 6 times 12 times 10 to power of 3. 12 times 5, this is equal to 60 times 10 to minus 3, or equal to 60 milliamps. So we between 6 and 8 here, equal to this is, there is a minus, sorry, 0 minus, okay, exactly, this is will be negative, so this will be minus, so this will becomes equal to minus 60. So here we will have minus 60, so it was 20 and then minus 60. Okay, and then everything is 0, so this everything will be good. This is how the current will look like. So this is minus 12, and here it is minus 60 milliamps. The last thing I'd like to cover today is, okay, the energy. This is how we solve. How much is the energy stored? We know it's stored energy, but how much is this? Okay, power is equal to the voltage times the current. This is something we know from before. And the current is CdV by dt, also something we derived today. Now, what is the energy? The energy W of the capacitor is basically the integration from 2 time interval or 2 time instance of B dt. The integration, the energy is nothing but the integration of the power. This is the definition of the integration or the energy. What is the 5 times 10 to minus 3? 5 to minus 3. I'm not following. Let me see here back. There is no 5 times. This is 5 times to minus 6, which is the capacitance. So there is no 5 times to minus 3. Okay, so this is the energy is equal to integration from. So usually we said, okay, find how much energy is stored in the capacitor from T1 to T2. T1 could be 0 at the initial time. So this is the energy stored in the capacitor. This is the formula. Now let's substitute here. So integration from T1 to T2. Now I will substitute P with its value. So it's VC dV by dt. So all of this is your P times dt. So dt will cancel. Now we agree that C is a constant. So I will take it outside the integration. So it becomes C integration of T1 to T2 of what? Of V dV. So basically this is V square over 2. So we'll have 1/2 V square, and there's a C here, integration from T1 to T2. So this is equal to 1/2 C times V at T2 square minus V at T1 square. Now, if we assume that the capacitor was initially not charged, there is no charge, and I'm just charging it right now without any charge before, so the energy in the capacitor will equal to 1/2 CV square. This is how much energy we can store in the capacitor. Last question here. Now and this is, by the way, will be your second question. So you will have 2 questions in the final from this set of notes. But they will not be, their weight will not be as high as the other questions. The other questions would be like the amplifier. This is one question, and these 2 will be like 2 small questions. One with you find the voltage or the current from the voltage or the current in a capacitor or an inductor using a formula or a graph. So all of these questions will do the same thing for the inductor as we move on. Second question will be, I will give you a circuit, capacitors and or inductors. I will tell you what is the energy stored in this. So here it says obtain the energy stored in each capacitor under DC conditions. So we have here a current source, and we want to have here how much energy stored in this capacitor and how much energy stored. We know the energy is equal to 1/2 CV squared. V is the voltage across the capacitor, which is basically the voltage between these 2 points for the 2 microfarad, and the voltage between these 2 points for the 4 microfarad. So I need to find this voltage and that voltage. This is the question, because C is given to us. Now this becomes like a circuit question, normal circuit question. Here now you can use nodal, KCL, KVL, voltage, current division. It is up to you. So first thing we need to do here is this capacitor will be changed into an open circuit. That is the only thing that you need to worry about. So look here. My first capacitor is changed to an open circuit. My second capacitor is also changed to open circuit. Now I want to find what is the voltage across this capacitor or across this open circuit or between these 2 points, and what is this voltage. Okay, so if I can find this current, as a matter of fact, I will be able to find this voltage. Very simple, Ohm's law, and we will see how we'll find this voltage. Now this circuit is becomes simpler because now we open circuit all these capacitors. So the current that goes here is equal to 0. So basically, what do we have here? We have, if we draw the circuit without those open circuits, it might a bit confusing us. So we have here 6 milliamp. So I have here one resistor, which is the 3 kilo ohm. We have the 2 kilo, and we have the 4 kilo. That's what we have. And I'm interested to find this current that goes through the 2 and the 4 kilo, which is this current I. When you look to this, I can even simplify it further. So this basically nothing but the 6 milliamp current source. This is the 3 kilo, and this is a 6 kilo. So basically two resistors in parallel, and I want to find this I. That's everything. So we apply current division. So your I, this I, is basically equal to the 6 milliamps times the other resistance, which is equal to 3 kilo ohm, divided by the summation of these together, 3 kilo plus the 6 kilo. This is current division. So this is equal to 6 milliamps times 3 over 9. So this is equal to this 3 to, so this is equal to 2 milliamp. So this current, as a matter of fact, is equal to 2 milliamp. Now, what is V1? V1 is this voltage between these 2 points. So your V1 is nothing but the 2000, 2 times 10 to power 3, times the 2 times 10 to minus 3, which is equal to 4 volt. This is the voltage here. So the energy stored in C1, WC1, is equal to 1/2 CV square. This is 2 millifarad. So this is 1/2 CV square is equal to 1/2 times C. C is 2 millifarad. So 2 times 10 to minus 3 times 4 square, which is equal to 16, and the unit will be millijoule. Let's see here, there is a question before I proceed. Where is V1 on the circuit? This is V1. This is V1. The V1 is, let's go back here. This is your capacitor. I want to find, this is the voltage across the capacitor. It becomes an open circuit. So this is my V1. Now I want to find V2, which is interesting. Now V2 is the voltage between this point and this point. However, this current is equal to 0. So this voltage drop is equal to 0. So basically V2 from this point to this point is the same as the voltage from this point to this point, because there's no voltage drop here. And the voltage between this point and this point is the voltage across the 4 kilo ohm. So basically your V2 is equal to the current, which is 2 milliamps, 2 times 10 minus 3 times 4 times 10 to power 3, which is equal to 8 volt. So this is the voltage across the 4 kilo ohm, which is the same as V2, because this voltage drop across the 5 kilo ohm is equal to 0. Okay, then the energy stored in C2 is equal to 1/2. Now this is C1, this would be C2 V2 square. So this is equal to 1/2. Now your C2 is equal to 4 millifarad. So 4 times 10 to minus 3 times the voltage, which is 8 square, and this will give us 128 millijoule. So with this, we solved this question, and I'll stop the recording now. So today we give you